Welcome to the deep dive. So today we're doing what we always do, taking some raw source material. This time it's updates from a pretty specialized scientific institution and really boiling it down for you.
Yeah, getting right to the core knowledge.
Exactly, giving you that shortcut to understanding a specific, maybe slightly complex area of science.
And today's focus is the National Center of Excellence in Analytical Chemistry, or NCEAC. It's based at the University of Sindh in Jamshoro, Pakistan. And looking at their materials, it's more than just paperwork. You really get a sense of an engine driving applied science.
That's a good way to put it. So our mission here is to understand how this center is, defining the cutting edge in analytical, environmental, and bioanalytical chemistry. What are their big research goals? And maybe more importantly, how are they actually translating that lab work into, real-world impact now?
Well, context is important here. NCEAC describes itself as one of the leading research hubs for analytical chemistry in Pakistan. And its location, about 150 kilometers from Karachi, near Hyderabad, isn't accidental. It's placed strategically near major industrial and population centers.
Ah, okay. So that gives it a kind of practical mandate, doesn't it? Addressing regional issues, health, environment.
Precisely. It sets them up to tackle real challenges on the ground.
Okay, let's unpack that mission then, starting maybe with the leadership. The director's message from Professor Dr. Amber Rehana Salangi, it seems very clear about the center's purpose. Focused on professional output, maybe, not just theory.
Oh, absolutely focused on output. The goal isn't just academic study. It's about providing these substantial MPhil and PhD programs, but highly specific ones, right?
Right, in those three areas, analytical, environmental, and bioanalytical chemistry.
Exactly, and the aim is clearly stated: pave the way directly for professional careers. So the curriculum, you have to assume, is built around solving actual problems.
Makes sense. If you're aiming to produce these high-level scientists for industry or government labs, you need a specific kind of student coming in. What sort of background are they looking for?
Yeah, they're quite specific. The MSM-Phil and PhD spots are really for people with a strong existing foundation in chemistry, biochemistry, or pharmacy.
Okay, so they need the basics down cold already.
Pretty much. They want students ready to jump straight into advanced analytical research. And, something else that jumps out for their updates is just the sheer pace they operate at. They seem to have a very active, forward-looking academic calendar, constantly bringing in new talent. For instance, their deadline for the 2025-26 session was back in May 2025. They plan ahead.
Right, always cycling through. So if that's the caliber of student, what are the big, maybe high-stakes research problems they're tackling immediately? Let's move past the structure and into the actual science. What tools, what methods are defining their work?
Well, they seem to be using the full modern toolkit. We're talking spectrophotometric methods, mass spectrometry, advanced chromatography, thermal analysis, the standard heavy hitters in analytical chemistry.
Okay, the workhorses. But is there anything strategically interesting in how they combine these? Listing techniques is one thing, but what's the unique capability they're building?
That's a great question. And one thing they explicitly mention is electrochemical methods, but they pair it directly with nanotechnology.
Ah, okay. That's interesting.
Yeah, it signals a major strategic focus, doesn't it? Developing these tiny sensors, new materials at the microscale. It's really integrating core chemistry with material science for analytical breakthroughs.
So connecting those high-tech methods back to the why, the bigger picture, it shows they're not just measuring stuff for the sake of it. They seem really grounded in real-world needs.
Exactly. Just look at their stated goals. Yes, developing new analytical methods, but critically, they're also invested in preparing new materials, specifically for identifying, and this is key, removing pollutants.
Right, so environmental cleanup is a big focus.
A very active focus. Finding ways to tackle industrial and environmental contamination using these novel analytical approaches and materials.
And it looks like the scope isn't just environment, it pushes right into human health, too.
It definitely stands both. On the health side, they're investigating how metal ions might play a role in physiological disorders. That's a direct link from analytical chemistry to potentially clinical insights.
And food. I saw mentions of food science.
Yes, food security is another pillar. They're looking at functional foods from local Pakistani fruits, doing detailed lipid analysis. It's about ensuring nutritional quality and safety.
That feels like a huge range to cover. Environmental remediation, health diagnostics, food analysis. Let's talk about the bioanalytical side. You mentioned nanotechnology. What breakthroughs are happening there at that biological interface?
Okay, yeah, this is where that nano pairing gets really exciting. They're developing nanobiosensors. So think tiny, ultra-sensitive devices that can pick up minute biological changes. And they're also working on ways to stick whole cells, or maybe purified enzymes, onto metal nanoparticles. This is really important for creating efficient, maybe reusable biological or chemical reactors.
Oh, okay, so more efficient processes.
Exactly. And then there's DNA biosensor technology that allows for really rapid, precise genetic ID and testing. It's genuinely multidisciplinary chemistry, biology, materials engineering, all coming together.
Okay, so moving beyond the lab itself, let's look at their recent impact. How are they proving their influence? Academic recognition has to be part of that, right? A center like this needs its published work to be credible.
And it seems their output is getting noticed. Their own journal, the Pakistan Journal of Analytical and Environmental Chemistry, PJAEC, got upgraded into the Higher Education Commission's top category, the X category, for 2023-2024.
That sounds significant.
It is. And maybe more tangibly for international reach, the journal hit an impact factor of 0.6 in the Clarivate 2022 ranking. Now, 0.6 might not sound huge in some fields, but for a specialized national journal, achieving a recognized impact factor means its articles are being cited, used, and considered credible internationally. It's a big validation.
And it looks like they're active internationally, too, not just publishing, hosting events, participating overseas.
That's right. They're organizing the 5th Pakturk International Conference on Chemical Sciences later this year, December 2025. That positions them as a convener, bringing scientists together. Plus, their director has been out there as a panelist or keynote speaker internationally, including a big agri-forum in China.
So they're deliberately putting their expertise on the world stage.
Seems like it. A conscious effort to engage globally.
Okay, connecting this back, maybe their real strength or a key part of their strategy is moving that knowledge from the academic sphere directly into, well, regulation and public health.
Yeah.
What partnerships are making that happen?
That seems to be a major focus. They've formalized key relationships through memorandums of understanding on use. They signed one with PCSIR Karachi, which is the Pakistan Council of Scientific and Industrial Research, late last year, and another critical one with the Sindh Food Authority, the SFA, back in June 2023.
Ah, the Food Authority. That's a direct link.
Exactly. These aren't just symbolic agreements. They seem to be the practical bridges between their analytical capabilities and immediate public good.
And did those connections lead to practical steps, especially with the food safety angle?
Immediately, it seems. The center successfully launched its first food testing laboratory. But they didn't just build it and walk away.
No.
No, they followed up right away with capacity building, a 2-day training session on advanced food testing techniques, and then the formal inauguration of the regional food testing lab just this past May. So they're providing the infrastructure and the expertise for regional food safety.
That's a very direct impact. And that shift from lab bench to policy, I noticed one of their senior people was involved in national policy discussions.
Yes. Professor Dr. Syed Tufail Hussain Shah. He was a panelist in a provincial consultation focused on eliminating industrially produced trans fatty acids, ITFAs, in Pakistan.
Right, trans fats.
Exactly. So their analytical and nutritional expertise is being fed directly into high-level public health policy decisions. It's a perfect example of that connection.
Okay, we absolutely have to talk about one specific achievement, that patent. It's the ultimate proof of turning research into something unique, protectable IP. The title is a bit technical.
It usually is.
Patent number 144,281, method for the fabrication of silver nanoparticles by unsaponifiable part of vegetable oil deodorizer distillate. Let's break that down.
Okay, so vegetable oil deodorizer distillate. VODD basically is a byproduct. It's waste, essentially, from refining industrial vegetable oils, usually low-value stuff.
Okay, waste from making cooking oil, more or less. And the unsaponifiable part.
That's just the fraction of this waste that doesn't react to make soap. So it's a specific component of this industrial residue.
So they're taking this specific bit of industrial cooking waste and turning it into what?
High-value silver nanoparticles. Yeah. Which, as we know, are crucial little things in advanced sensors, biosensors, antibacterial coatings, all sorts of high-tech applications.
Wow. So that's not just clever chemistry, is it? It's almost alchemy, turning waste into something valuable using nanotechnology.
It's a fantastic example of applied chemistry and, frankly, smart economics, taking industrial trash and creating high-tech functional treasure. It really highlights that nanotechnology focus again.
That's a really profound value jump. And alongside all this cutting-edge research and patenting, they're also making sure their basic operations, their labs, meet global standards. They ran workshops on ISO/IC 17025. Why is that standard so important?
17025. That's the international benchmark for the competence of testing and calibration labs. If you're setting up a new regional food testing lab like they did,
Right.
and you want the results from that lab to be accepted for regulatory decisions, maybe even for trade, the data has to be rock solid, internationally recognized,
Yeah.
defensible,
So implementing that ISO standard gives their results credibility.
massive credibility. It tells regulators, partners, everyone that their analytical work is accurate, reliable, and meets the toughest global quality standards. It underpins everything else they're doing in safety and policy.
Okay, so pulling it all together, the major takeaway seems to be that NCAC isn't just a traditional university department. It's operating as this highly integrated hub.
Yeah, it really seems to be bridging that gap between complex, frankly, bleeding-edge science, things like DNA biosensors, supermolecular chemistry, and getting it directly into applied fields.
Fields with immediate impact, like food safety, cleaning up pollutants, influencing health policy.
Absolutely. They seem to be acting as this central node for analytical science in their region, generating both the sophisticated research and the practical, internationally validated results, and doing it pretty fast, it seems.
That scope and that pace really do stand out from their updates.
Which leaves us, and you listening, with a final thought to maybe chew on, directly inspired by that patent work. If NCAC can take a waste stream like VODD, something most industries would just try to dispose of cheaply and turn it into high-tech silver nanoparticles. Just imagine the potential globally. How much hidden value, how much research potential might be locked up in common, low-cost industrial waste streams everywhere.
So looking for value where others see waste.
Exactly. Could the next big breakthroughs in materials science or even other fields come not from finding rare new resources, but just from looking much, much smarter at the stuff we currently throw away? Something to think about.